Hello everyone, welcome to Digital Image Processing class. In this video, we will introduce 6-bit color code and how to use 6-bit color code to represent a group of colors in an RGB image. As you have learned that histogram can be used to describe the intensity distribution of a gray level image. A pixel in an RGB color space is composed of 3 primary colors, that is, red, green, and blue, each of which has 256 different intensity levels. Therefore, in the RGB color space, the total number of colors is 256 to the power of 3, which is more than 16 million colors. With so many different colors, how can we describe the color distribution in an RGB color image? We can, of course, build an image histogram with 256 to the power of 3 bins. However, this approach is inefficient due to the fact that creating and handling an image histogram with such a huge number of bins is a time-consuming process. To reduce the number of bins, one of the solutions is to group similar colors as one group and assign the group with an ID number, which is known as color code. For examples, on the screen, we show 3 color groups. Similar red colors are grouped together and assign a group ID such as 48 as a color code. Once we can put similar colors in the same group, we can greatly reduce the number of bins in the histogram. This leads to the next question, that is, how can we determine similar colors? In order to determine color similarity, we need to further investigate the composition of RGB color. As you know that each color is composed of 8-bit red intensity, 8-bit green intensity, and 8-bit blue intensity. For each primary color, as shown on the right of the decimal intensity level, can be represented as a corresponding binary number, as shown on the left. For example, intensity level 0 and decimal can be represented as 00000000 in binary. Similarly, intensity level 64 and decimal can be represented as 01000000. In a binary number system, the leftmost digit is called the most significant bit, and the rightmost digit is known as the least significant bit. This is because when the most significant bit is changed, the number has a big change. Contrarily, when the least significant bit is changed, the number has a small change. For example, decimal number 0 can be represented as a binary number 00000000. If you change the most significant bit from 0 to 1, the number becomes 128. If you change the least significant bit from 0 to 1, the number becomes 1. We can utilize this property to group similar colors. As you can observe from the example, when the least significant bit is changed from 0 to 1, the intensity level increases by 1. It would be pretty difficult for eye to see the slightly difference. Instead, in case we change the most significant bit from 0 to 1, the intensity level increases to 128. This indicates that if we keep the two most significant bits and ignore the remaining 6 least significant bits, we can group the 256 different intensity level into 2 to the power of 2, which equal to 4 groups for each of the RGB channel. Therefore, when combining RGB channels, we will have 4 to the power of 3, which is equal to 64 color groups. This leads to the concept of 6-bit color code. In this slide, we are going to show you how to construct a 6-bit color code. As we previously described, the most significant bits from R, G, and B channels can divide each color into 4 groups. So assume we have a pixel with the RGB value, which is originally 213 for red, 127 for green, and 170 for blue. The subscript at the bottom right corner indicates that's the decimal value. As we previously described, a decimal value can be converted into a binary string. So therefore, 213 converted into binary string, we will have 11010101. 127 in green, we can convert it into 01111111. The blue channel, the intensity level 170 in decimal, we can convert it into 10101010. The subscript at the bottom right corner indicate these are binary. As we previously described, we will only take the most significant 2 bits from the red, green, and blue. So from the red channel, we will take the first 2 digits on the left, which is the 11 in red. Similarly, for the green channel, we will take the left 2 bits, which is 01 in green. From the blue channel, we take 10 from the left 2 bits. So the red, green, blue, and we can combine them as a single 6-bit string. From left to right is red, green, and blue respectively. So as you can see, the red 11 will be on the left, the green 01 will be in the middle, and the blue 10 will be on the right. Then we can convert the 6-bit string back to its decimal value. So once we convert into decimal value, we can get 54 in decimal. So this coding process enables us to describe each color using 6 bits, which corresponding to 2 to the power of 6, which is 64 color categories. In this exercise, please answer the following question. What is the 6-bit color code for the following colors? When RGB values are 255, 255, and 255. Second, what is the color code for the RGB value 128, 32, and 255? Question number 3. What is the color code for the RGB pixel with the 32, 128, and 255? Question number 4. What is the color code for the RGB value 255, 128, and 32? Question number 5. What is the 6-bit color code for RGB value 255, 32, and 128? The last question, what is the 6-bit color code for the RGB value 0, 0, and 0? So, did you get the right answer? The first step to obtain 6-bit color code from the RGB values of a pixel is to convert the RGB values from decimal to binary. A MATLAB function named DEC2BIN, decimal to bin, can take a decimal value as its input and convert the decimal value to corresponding binary value as a string. Please notice that a string in MATLAB is encompassed by a pair of single quotation marks. The DEC2BIN function is overloaded. The first usage is that we can call DEC2BIN function with a decimal value as the only input parameter. The returned binary string has no leading zeros. For examples, when converting a decimal value 196 to the corresponding binary string, we will receive a 8-bit binary string 11000100. However, when converting 32 to the corresponding binary string, we will have a 6-bit binary string 100000. To construct a 6-bit color code, we need to take the two most significant bits from an 8-bit binary string. Therefore, if the function returns a 6-bit binary string, the two significant bits 00 and the 8-bit binary string should be the two leading zeros. To overcome the missing leading zeros, the second usage of the DEC2BIN function is introduced. When calling the decimal to binary DEC2BIN function, we can provide a second parameter which indicates the total number of bits should return, so that the MATLAB function will automatically add the leading zeros. As shown in the examples at the bottom, when calling DEC to BIN function with the second input parameter number 8, the returned binary string has exactly 8 bits. The second step to construct a 6-bit color code is that we need to extract the most significant 2-bit from an 8-bit binary string. As aforementioned, MATLAB stores binary value as a string. Therefore, you will need to learn the skill to access particular substring from a string in order to get the most significant 2-bit from a binary string. Assume that we have a regular string. For example, a string variable str is assigned with a string constant, that is A, B, C, D, E, F. To access a particular substring from a string, we can use string with str with a parenthesis 1. In this case, you will get the character A. If you change string str to 2, then you will get B. Because in the parenthesis is the index, the subscript for the element in the string. Similarly, you can also use str with a parenthesis and you can put 1 column 3. So this means you are going to access the element 1 to 3 in the str. In this case, you will get A, B, C. Similarly, to access string 3 to 5, you will get C, D, E. Now, you have learned how to access a substring from a string. You can apply this skill to extract the most significant 2-bit from the 8-bit binary string. The third step to obtain a 6-bit color code is to combine the 3 most significant 2-bit extracted from the R, G, and B values. To combine the 3 substrings extracted from the R, G, B values to form a 6-bit binary string, we can simply concatenate the 3 substrings as shown on the screen. Assume we have 3 substrings str1, str2, and str3, which stores AB, CD, and EF strings respectively. We can concatenate them by placing them within a square bracket. So once you place str1, str2, and str3 within the square bracket and assign to a string str, now the str will hold A, B, C, D, E, F as a single string. To this end, you have learned how to convert decimal value to corresponding binary string. You also know how to extract the most significant 2-bit from the binary string and how to combine the extracted substrings as a new binary string. Now, it is time to convert the new binary string to decimal value. To convert a binary string to the corresponding decimal value, we can use BIN to DEC function in MATLAB. The bin to dec function takes the binary string as its input and returns the corresponding decimal value. As shown on the screen, the example, the input binary string is 100011. So you can call the function by passing the binary string, and then you will receive its corresponding decimal value. So far, you have learned how to convert RGB values of a pixel to its corresponding 6-bit color code. Please create and implement a function named RGB to 6cc in MATLAB to convert RGB value to 6-bit color code. The hint is that the RGB to 6cc function should be able to take R, G, and B values as its input and return the corresponding 6-bit color code as the output. The RGB to 6cc function plays an important role in your midterm and final project. So please focus on how to implement this function and try to develop your own solution as soon as possible.